Hey guys, welcome to the last section that we'll study before we kind of start wrapping up the unit. We're talking about RC circuits, and most specifically, we'll look at a capacitor in a circuit first, and then when I get back on Thursday, we will look at analyzing capacitors in more complex circuits, and then using the KVL, Kirchhoff's loop laws, to analyze more complex circuits. But we all kind of remember what a capacitor is. If we need to go back and look at that, we can. But just remember, it works kind of like this. It's connected to a circuit. There's a battery. There's an open switch. That's the S. And then my light bulb, I just kind of used a real basic drawing here with the L representing the light bulb. And here, the switch is currently open. The battery has a voltage. And the capacitor has zero potential on it. Zero potential difference or zero voltage. When it first starts out, it's all electrically neutral, and the light bulb is not lit. There's nothing going through it. When we close the circuit, or close the switch, immediately electrons and current starts flowing. The charges, or the electrons, move through the battery and are deposited on the bottom plate of the capacitor. Remember, we're using conventional current here, defined as the flow of the positive charge, so its direction is clockwise in this case. Remember, the battery tells us which way that's pointing. So immediately after the switch is closed, the maximum amount of current is flowing, and the light bulb is at its brightest. As the plate charges, the potential difference between them increases and oppose the battery's potential difference, and the current starts decreasing and is zero when the two potentials are equal in magnitude. So remember, once the capacitor becomes full, it no longer lets charges pass through it. The light bulb gets dimmer until the current stops and the light bulb goes out. The charge on each plate is now at a maximum. So that is really similar to our little circuit that we tried to design a little while ago. So now we added a circuit across the middle of it. So we added a switch that you can close the circuit now. And the branch is now letting the current discharge from the capacitor. Electrons start flowing, but at this time in a clockwise direction. Conventional current flows in a counterclockwise. So once again, the capacitor kind of behaves like a battery, but things have to flow out of the negative side of it. The potential difference decreases as the capacitor is discharged. This is a pretty fast process, if you remember how our little circuit was working. Unlike a battery that maintains its potential by the chemicals going on in it. And what happens to the light bulb? Well, as the potential difference decreases to zero, the current decreases using Ohm's law until no current flows. The capacitor is now fully discharged. The light bulb gets dimmer and dimmer until it turns off. So how do capacitors behave? And I think they are distant cousins to resistors. Circuits with multiple capacitors can be redrawn just like a single capacitor, just like what we did with resistors. By reducing the circuit this way, the circuit becomes easier to study, like we saw with our study of resistors. And this is called equivalent capacitance, and they happen to be in series and parallel. So let's first take a look at parallel capacitors set up in a parallel format. The voltage across each capacitor, well, it's the same. So we're going to have the same idea with capacitors as we have with resistors. These parallel capacitors will have the same voltage drop across them. The charge on each capacitor is Q. And when you have capacitors in parallel, you're simply adding more area for the charges to be stored, and the equivalent capacitance of the circuit increases. So here's a quick little math derivation how that works. Since the voltages are the same and the Q's are the same for each one, we have C1 plus times V plus C2 times V. That's the charge. And divide both sides by V, you get the total capacitance is C1 plus C2. So in other words, for capacitors in parallel, you're just going to add them up, the same process we used for resistors in series. So it's kind of the same, just different here. Capacitors in parallel are added together like a series resistor. Well, let's take a look at a series capacitor. Here, the voltage is, everything is added across those, just like the series resistors were. And then the charges would be the same. So, kind of taking a couple of shortcuts here, but for capacitors in series, we do the inverse addition. The equivalent capacitance of the circuit ends up decreasing when I add capacitors in series. So just as a quick rehash here, capacitors in series are added like resistors in parallel, and capacitors in parallel are added like resistors in series. So we have to be mindful of how they're set up. And one of the things that we're going to have to look at for our assignments on this is to make sure we understand how much energy is stored in a capacitor. So make sure we take a look at our formula sheets to know which one, how that behaves, and finding equivalent capacitance based on what the circuit is doing. Okay, that was kind of quick and fast, but I hope that made sense, and I will see you guys soon. Thanks for watching. Bye.